Remember back in single variable calculus, we could find the maximum and minimum of a function by setting the function's derivative equal to 0 and solving for x. The idea was that a function attains a local max or min where its tangent line is flat. This carries over in the world of multivariable functions to setting the gradient of our multivariable function to 0, which is equivalent to setting all partial derivatives equal to 0 and then solving the resulting system of equations. This works fine as far as it goes, but very often in real-world settings, we have additional constraints that restrict the values of our variables. This means our independent variables x and y are not free to roam around anywhere we like in the plane, and are restricted to some region or curve and are not allowed to take on values outside of it. As a result, the graph of our function is now a surface with a boundary, and the absolute maximum or minimum of the function could occur on it, and in fact, it often does. This can be a problem because if the max or min does occur on the boundary, the gradient doesn't have to be 0 there. That is, the surface doesn't have to be flat there. This is just like how in single variable calculus, when finding the max or min of a function on some closed interval, you had to check the endpoints, or boundary, of the interval in addition to the flat points when determining the absolute max or min, because the curve did not have to be flat at the endpoints. Likewise, in addition to the flat points on the surface, we also have to check the boundary of the surface for local maxes and mins. However, it turns out finding maxes and mins on a boundary curve is not as easy as it might look at first glance, and so finding a good way to do that is what we'll focus on for the rest of the video. So what makes this so difficult? Back in single variable calculus, it was pretty straightforward to deal with a boundary because with single variable functions, you only have two boundary points to check, the left endpoint and the right endpoint. And so you could just evaluate the function at both to see if either of them were an absolute max or min. But with multivariable functions, the boundary is a curve, and a curve contains infinitely many points, which means we can't just plug all of them in one by one to see which is the highest and which is the lowest. One way you could deal with this is to parametrize the curve, which means varying a parameter t that moves a point along the curve and keep track of the height of the point as t varies. This would turn the problem of finding the max or min on a curve in 3D space into a single variable calculus problem of finding the max or min height as you vary the single variable t. Although that's one way to do it, the method we'll look at in this video is a bit different. It's called the method of Lagrange multipliers, which is a pretty clever trick that allows us to avoid the hassle of parametrizing the curve and then having to solve a single variable max and min problem. How can we do this?
Okay, hello lecturer. So now let's coming up to the problem 1. I will show this problem, and according to the method of Lagrange multiplier, so I will find the maximum or minimum of fxy subjected to the constraint x squared plus y squared minus 2 equal to 0. So first we will have the formula of the Lagrange multiplier. The gradient vector of fx0, y0 will equal to lambda multiplied with the gradient vector of g x0, y0, and the gradient vector of g will equal to the 1 to matrix 2x to y, and the gradient vector of f will equal to the 2 to matrix 2x minus 2 4y power to 3 and minus 4. Otherwise, you can see this will be the derivative of gx and gy, and here we will have the derivative of fx and fy, and then we will have this equation, and from this equation we will divide it into two equations, and we will divide the equation 1 and 2 to 2 So we have x minus 1 will go to lambda multiplied to x, and 2y power to 3 minus 2 will go to lambda multiply y. And as you can see, lambda will equal to x minus 1 divided by x, and lambda will also equal to 2y power to 3 minus 2 per r divided by y, and we can see is equal to each other, and I will multiply it here, and of course we will have this. X will equal to the square root of 2 minus y power to 2 in here, the constraint, and then we substitute it into the equation above, and the equation will become this. So when we use the calculator to solve the equation, we will see that there will exist two results, y equal to 1 and minus 1, and from this we will find out that x will equal to 1, and with each value of y we will see the different value of fxy. So we can see that 11 will be the minimum value of fxy, and 19 will be the maximum value of fxy. In here we will see that in the similar area where when this function and this constraint, we will see that the vector fxm, fym, and the vector of the gradient vector of gxm and gym is parallel to each other. I also printed to wherever we will see the similar between them. Okay, so now I have finished to prove it, the problem 1. Thank you for listening.
Gradient descent is the process by which machines learn how to generate new faces, play hide and seek, and even beat the best humans at games like Dota. But what exactly is gradient descent? To answer that question, let's say you are trying to train your computer to listen to an audio file and recognize 3 spoken commands based on a labeled dataset. The first step is to formulate this machine learning task as a mathematical optimization problem. For example, you can work with a neural network whose weights are unknown variables, whose input is an audio data, and whose output is a vector of size 3 where each entry represents how much the neural network thinks the audio corresponds to each command. Then, for each example in the dataset, you compare the output of the neural network to the ideal output. Take the difference, the square, and then the sum, and you get the cost of a single training example. By taking the sum over all training examples, you get the overall cost function. And the problem now becomes, how do we find the right value of theta that makes this cost function as small as possible? And this is where the second step, or gradient descent, comes in. And you might ask, why do we need to invent an algorithm for this at all? Can't we just plot the function and point to the minimizer? Well, theta usually has many more entries than just 2. And in that setting, it's hard to see what the function looks like. So what can we do? The insight of gradient descent is that while we cannot get a look at the whole function all at once, we can easily evaluate the cost function at an arbitrary point. And with a process called backpropagation, we can also evaluate the negative gradient of this cost function and take a small step in that direction. Gradient descent continues in an iterative fashion. It computes the negative gradient at the new point, takes a step in that direction, and so on and so forth. The intuition behind every step is that the gradient of a function gives you the direction that increases that function the most. So by taking a small step in the opposite direction, you can hope to make the function decrease at each iteration. Gradient descent, as I just presented it, is known as vanilla gradient descent, because several variants have been developed throughout the years to improve it. In stochastic gradient descent, instead of taking the sum over all training examples when taking the gradient of the cost function, which can be expensive when the number of examples is big, we can take a small random subset at each iteration. Adaptive gradient descent picks a different step size for each component of data, and this can be extremely useful when data is sparse, like text data and image data. Momentum gradient descent keeps track of previously computed gradients to build up momentum and accelerate conversions to the minimizer. This was gradient descent in under 3 minutes.
On question 2, we will find local minima of equation y equal to x minus 1 multiply x minus 2 multiply square minus x minus 3. First step, we will find the derivative of yx. We will have this function, and second steps, we use the Lagrange multiply to find the local minima of the function. We will set up a linear function x1 equal to x0 minus a y0 with a starting point. In this case, I choose a equal 0.1 and x equal 0. And when I replace a and x0 to the equation, I can calculate the x1, and I continue do it for x2, x3, and x4. After doing a lot of x, I see that the result is approaching 3. As you can see here, I sketched the equation for x1 here and x2, x3, x4. We can see that the linear equation is approaching the local minima, which is 3 here. So, and the more x we do, the result will approximately 3, and finally it will equal to 3.